A very nice welcome to the Bharatiya Krishak quantum physics classes. And in the previous class you know about the de Broglie hypothesis. Let's again see the de Broglie hypothesis.
Matter can exhibit wave-like properties. Why don't macroscopic objects appear like wave to us? So to understand this, we should make some calculation. Consider a ball of mass which 10 to the power minus 3 kg moves with a velocity of 10 to the power minus 2 meter per second. Then what will be the de Broglie wavelength of the ball? So let's calculate it. The de Broglie wavelength is given by lambda equals to h by p equals to 6.626 into 10 to the power minus 34 joule second divided by 10 to the power minus 3 kg into 10 to the power minus 2 meter per second, which comes out to be, that is lambda value, 6.626 into 10 to the power minus 29 meter. Clearly, this wavelength is too small to be detected experimentally. Hence, we can say that matter waves are associated with macroscopic objects. However, their wave character is not observable. Thus, they can safely be described as a particle under all circumstances. Now, see another example. That is the de Broglie wavelength of 100 electron volt electron and a 1 mega electron volt neutron. So here we calculate the lambda E, that is de Broglie wavelength of electron, is given by formula h by under root 2 m naught E. The value is now 6.626 into 10 to the power minus 34 joule second, value of H, and 2 into 9.109 into 10 to the power minus 31 kg into 100 into 1.6 into 10 to the power minus 19 joule, whole of power 1 by 2, which comes out to be 1.227 10 to the power minus 10 meter. So de Broglie wavelength of 100 electron volt electron is 1.227 into 10 to the power minus 10 meter. Similarly, for neutron, lambda n equals to 6.626 into 10 to the power minus 34 joule second, and putting on other values like mass of neutron 1.675 into 10 to the power minus 27 kg and 1 mega electron volt means 10 to the power 6 into 1.6 into 10 to the power 19 joule. So using this value we get lambda n, lambda sub n, value of neutron, wavelength of neutron 2.862 into 10 to the power minus 14 meter. So clearly the wavelength to be about 1.2 into 10 to the power minus 10 meter for the 100 electron volt electron and 2.9 into 10 to the power minus 14 meter for the 1 mega electron volt neutron respectively. Clearly, we see that the wavelength of the matter waves associated with 100 electron volts electrons lies in the X-rays region and is of the same order as the atomic spacing in a crystal. The electron waves like X-rays are therefore expected to undergo diffraction by crystal. On the other hand, the wavelength of a 1 mega electron volt neutron is too small for observing the diffraction by a diffracting grating. However, low energy neutrons, say 100 electron volt neutrons, would have a wavelength in the X-ray region and then their diffraction pattern can be obtained. Thus, we see that for the motion of a macroscopic object, the de Broglie hypothesis does not does not change the classical description as developed by Newton. But for microscopic objects, the wavelength of matter waves are long enough to undergo observable diffraction. The diffraction of matter waves was observed experimentally as early as in 1927. Now we see the experimental evidence for the existence of matter waves. The first experimental demonstration of matter waves came 3 years after de Broglie advanced his hypothesis and was accidentally obtained by two American physicists, Clinton J. Davison and his assistant L.H. Jarmer. They were studying the scattering of electrons by crystal using the apparatus for diffraction. Now, electron from an electron gun were accelerated by a positive electrode maintained at V volts as compared to the filament. The accelerated beam of electron was incident on a strip of nickel containing many crystals, and the number of electrons scattered in various directions was then measured. A smooth variation in the intensity of the scattered electron with the angle was observed. Midway through the experiment, an accident occurred which permitted air to enter into the vacuum tube containing the strip. This resulted in the formation of an oxide film on the surface. Davison and Jarmer were then forced to heat the strip to a very high temperature in order to reduce the oxide. This heating and slow cooling had the effect of turning the polycrystalline nickel sample into a large single crystal. After this forced heat treatment of the sample, the experiment was repeated. The experimental result this time were quite different from those obtained before the accident. The intensity of a scattered electron showed some sharp maxima and minima at certain angles, which were found to depend upon the electron energy and hence upon the accelerating voltage. This pattern was similar to a wave diffraction pattern. Some typical results from these experiments can be shown. Davison and Jarmer found that the angular peaks of scattered electrons could be explained as a diffraction of electrons by atoms if the regular arrays of atoms in the nickel crystals are regarded as a diffraction grating. Now, diffraction of electrons using Bragg's analysis developed for X-ray scattering and the angle of scattering at which pronounced peaks are produced. They calculated the wavelength of electron waves. They finally found very good agreement between their values of wavelength and those given by the de Broglie hypothesis. Thus, the validity of the de Broglie hypothesis was established very good. Established nicely. In one particular experiment, the electron beam was accelerated to a potential of 54 volts and the maximum intensity was observed at an angle of 65 degrees between a particular family of crystal planes and the incident beam, that is a scattered beam. The spacing between the crystal planes as measured by X-ray diffraction techniques was found to be 0.91 angstrom. Now calculate the wavelength of the electron waves from these electron diffraction data. The phase difference between waves coming from adjacent scattering planes of a crystal is given by 2 pi by lambda into 2d sine theta, where d is the spacing between surface. For constructive intermissions, we therefore have 2 pi by lambda into 2d sine theta equals to 2 pi n, where n equals to 1, 2, 3 dash dash dash. So we get lambda equals to 2d sine theta divided by n. Now, using above data in this equation, we get lambda equals to 2 into 0.91 angstrom sine 65 degree equals to 1.65 angstrom. So now compare the value of lambda with the corresponding value predicted by de Broglie hypothesis. The de Broglie wavelength of an electron accelerated by a potential of V voltage given by lambda equals to h by p equals to h by under root 2 me v naught v 12.264 divided by v volts under root v volts angstrom. Hence, the wavelength of a 54 electron volt electron is lambda equals to 12.264 divided by under root 54 angstrom equals to 1.67 angstrom. Here we notice that the agreement between the two values of the wavelengths of electrons. Within months of the discovery by Davison and Germer, a British physicist J.P. Thomson also discovered diffraction effect with a beam of highly energetic electrons. In 1928, Thomson repeated his experiment by using platinum then the celluloid film. The diffraction is observed with the polycrystalline metal, while were found to be exactly similar to those observed for X-rays of the same wavelength as that of electron. This experiment of Thomson's had provided even more convincing evidence in the support of the de Broglie hypothesis. De Broglie was given a Nobel Prize in Physics in 1929, and the same was awarded to Davison and Thomson in 1937. It is of interest to note that Sir J.J. Thomson was awarded Nobel Prize for Physics in 1906 for discovering the electron as a particle carrying negative electrical charge, and in 1937 his son J.P. Thomson got the same prize for establishing the wave nature of electron. With stably designing experiment, the wave-like behavior of particles such as alpha particles, proton, neutrons, etc. can also be established.
So here you watch how much Bharatiya Krishaks, farmers, laborers are intelligent. Even you don't know about these farmer and Krishaks, laborers. They all are quantum physicists in Bharat.